Derivations of equations of motion. We all know the equation. V is equals to u plus at. V is the final velocity, u is the initial velocity. A acceleration, t is the time. So we will be doing this by graphical method. First equation of motion. Consider an object moving in a straight line with uniform velocity u. Here you can observe that the object has not started from its origin. We can see that velocity time graph has not started from origin. It has started from point A, which is not the origin. When initial velocity is u, give it a uniform acceleration. We all know that uniform acceleration means body travels in a straight line and velocity increases. So the object velocity increases as a result of the acceleration to final velocity in time t, and s is the distance covered by the object. The graph depicts the velocity time graph of the object motion. On graph you can observe that OA equals to u equals to initial velocity equals to dc. OE equals to v equals to final velocity equals to bc. OC is the time. The acceleration of a moving object is given by the slope of velocity time graph, area under Vt graph. By definition of acceleration equals to change in velocity by time. A equals to final velocity minus initial velocity by time. Here final velocity is bc and initial velocity is time is oc. A equals to v minus u by t. V minus u equals to at. V is equals to u plus at. This is the first equation of motion. So this was all about first equation of motion that we have derived from graphical method using this velocity time graph. Second equation of motion, also known as position time relation. In velocity time graph, you can observe that u is the object initial velocity and v is the final velocity. A be the acceleration produced in the body. The area enclosed by velocity time graph. Here OA equals to u equals to initial velocity. BC equals to v equals to final velocity. OC is the time. OC equals to t equals to time taken. Let the acceleration of the body changes at a uniform rate and it covers a displacement of s in time t. From the graph, displacement equals to area under graph AB. So displacement equals to area of trapezium OABC. We will be finding whole area of the trapezium by first adding the area of triangle and finding the area of rectangle. Area of triangle ABD and area of rectangle OADC. Then adding up these both areas, we know the formula for area of triangle as well as for the area of rectangle. Area of triangle is given by half into base into height. And area of rectangle we already know, that is length into breadth. So here displacement equals to half into base into height plus length into breadth. S equals to half into, here base is AD and height is BD plus length area of rectangle equals to length into breadth. So here length is OC and breadth is OA. S equals to half into AD into, now this BD here is given by BC minus DC. We will subtract this, plus OC into OA. S equals to half into T. AD is time, because here you can see that AD is parallel to OC. So if OC is time, then AD is also time. So S equals to half into T into BC is V and DC U, plus T into U. S equals to half into V minus U into T plus UT. This is the first equation. Here we already know the first equation of motion, that is V equals to U plus AT. So V minus U equals to AT. This is the second equation. Now on substituting this equation 2 in equation 1, we will have S equals to half into V minus U into T plus UT. We already know that V minus U equals to AT. So in the place of V minus U, we take AT. S equals to half into AT into T plus UT. S equals to half into AT square plus UT. Now rearranging the terms, we get S equals to UT plus half into AT square. So this is the second equation of motion. Third equation of motion is also known as position-velocity relation. Here in velocity time graph, AB is the straight line. Then we have drawn a perpendicular line, that is BC. Let U be an object's initial velocity and A be the acceleration produced in the body. The area enclosed by the velocity time graph gives distance traveled in time, T. So we all know the third equation of motion. Here V is the final velocity, U is initial velocity, A is the acceleration, S is the displacement. Here OA equals to U equals to initial velocity, BC equals to V equals to final velocity, OC equals to T equals to time taken. OC is the time. Let the body covers a displacement of S in time T. From the graph, displacement equals to area under the graph AB. So S equals to area of trapezium OABC. Area of trapezium equals to half into base 1 plus base 2 into height. Here base 1 is OA, base 2 is BC, that is final velocity, into OC. Area of trapezium OABC equals to half into U plus V into T. This is the first equation. We all know the first equation of motion, that is V equals to U plus AT. So T equals to V minus U by A. This is the second equation. On substituting equation 2 in equation 1, we get S equals to half into U plus V into T. In the place of T, we will be writing V minus U by A. So half into U plus V into V minus U by A. S equals to u plus v into v minus u by 2a. S equals to v square minus u square by 2a. 2as equals to v square minus u square. This is the third equation of motion.